Thank you for coming to my talk. What you see may not be what you get. UCB Bandit algorithms robust to epsilon contamination. This is joint work by myself, Niss, and Ambuj Tewari at the University of Michigan. This work is motivated by the use of bandit algorithms in education, particularly inspired by Joseph Williams and others' 2016 paper. It is not particularly controversial to say that when soliciting feedback from students, not all answers are mindful or effortful. When using student feedback as bandit rewards, this can cause some rewards to be uninformative. This experience is well documented in survey data, where 8 to 12% of responses are estimated to be inattentive, and generally these inattentive responses are not a random sample of the response space, which means they cannot simply be ignored as they are likely to skew results. While we are interested in applications in contaminated bandits in education, uninformative rewards can be a problem in many other areas. For example, anytime rewards are human feedback, such as surveys and self-reporting, or when there can be automated contamination, such as apps designed for privacy protection but obfuscate by clicking on all ads, or malicious adware that clicks on particular ads to influence marketing algorithms, or in measurement areas such as what many of us see on wearable sensors. This work aims to provide simple, intuitive algorithms to account for when there is contaminated rewards, particularly when there is relatively small time horizon, which would be expected when using it by educational practitioners. The play is similar to that of full stochastic bandits. We use R as the stochastic reward, C as the contaminated reward, and X as the observed reward, which is either R or C. For a fixed number of actions K and time horizon T, at each time step, the learner picks an action, a stochastic reward R is drawn from a fixed distribution, the adversary chooses a contaminated reward, and then the learner sees only the observed reward. How much knowledge the adversary has, bounds on contamination, and when contamination can occur differs across work in this area. We are focused on epsilon contamination, which constrains the adversary such that at each time step, every action has only up to an epsilon fraction of contaminated rewards. For the sake of time, I will not list out all previous works, but will highlight that our work is most similar to that of Kapoor and others' 2018 paper, which includes a modified UCB algorithm for Gaussian rewards that uses the median as a robust mean estimator with an adjusted exploration term. We expand this intuitive idea to use two other robust mean estimators for sub-Gaussian rewards. We allow our adversary to have full knowledge, including of the policy, optimal action, previous, current, and future rewards, and to contaminate at any time point with unbounded contamination. Again, we constrain it such that for all t, every action has only up to an epsilon fraction of contaminated rewards. To get a UCB algorithm robust to epsilon contamination, we use two robust mean estimators and adjust the exploration term to use their finite epsilon contamination concentration bounds. Our robust mean estimators are the alpha trimmed mean, which is mean after moving an alpha proportion of the largest and an alpha proportion of the smallest sample point, and the alpha short mean, which takes the mean of the shortest interval containing 1 minus alpha points. The epsilon contamination concentration bound for the trimmed mean is derived from a previous paper by Liu and others in 2019, and we derived the alpha short bound in our paper. We leave the details of these bounds to our paper. Our contamination robust UCB algorithm requires knowledge of an upper bound on contamination as well as an upper bound on the sub-Gaussian constant. While not always reasonable to expect knowledge of these numbers, there are many applications where previous work has already given insight, such as the 8 to 12% contamination and survey data mentioned earlier, as well as work for things such as mechanical Turk. If rewards are bounded, this also immediately gives an upper bound on the sub-Gaussian constant. In simulations, we show that our algorithms are somewhat robust if these constants are misspecified. Our algorithm is as follows. Pick each action once. Then, for the rest of play, pick the action that maximizes the robust mean estimate plus an exploration term. You can see our exploration term is quite similar to UCB1, but uses a different constant that includes alpha. To analyze regret in the setting of contaminated bandits, we argue that only the true stochastic reward should be considered. If the observed reward contains no information on the performance of the action, then it should not be used to compare performance of a policy. Therefore, we measure regret only compared to the stochastic reward. For a fixed K and P, a small enough epsilon, our contamination robust UCB algorithm, using either the trimmed mean or short mean, obtains regret on the order of square root of KTlogT. The limit on the size of epsilon ultimately depends on the size of the suboptimality gap. If epsilon is too large, then the distribution of rewards for the optimal action and the runner-up action can be indistinguishable. We provide a simple example of this in the paper. We structured our simulations to be close to that of implementing something in a large university class. Therefore, we chose 5 actions and a time horizon of 1,000. Each graph shows the average regret over 10 trials. Rewards are binomial, such as the distribution might be for a Likert scale, with the suboptimality gap as 1. All suboptimal actions have the same distribution. We chose a simple adversary, which contaminates at every iteration with a probability of epsilon, and made it malicious, so that it gives the optimal actions small rewards and suboptimal actions large rewards. We compared against the standard stochastic algorithm UCB1, an adversarial algorithm EXP3, two best of both worlds algorithms EXP3++ and 0.5 Tsallis-Inf, as well as rUCB MAB, which is the algorithm for contaminated bandits with Gaussian boards we mentioned earlier. These graphs increase in the amount of contamination from left to right. We can see that UCB1 continues to do well when there is only 5% contamination, but degrades to essentially linear regret when there is 10% contamination. The best of both worlds algorithms perform similarly, though consistently worse. Our algorithms sUCB and TUCB do consistently well along with rUCB and MAB. The simulation shows a small amount of contamination may possibly be ignored and standard algorithms used, but large amounts of contamination severely degrade performance and must be taken into account. These graphs aim to show that if there is no contamination, how much are you losing in performance if you use a contamination robust algorithm, or at least the three that we show here. You can see in plots B and C that there is little performance degradation compared to A, even though the amount of contamination is not specified. So if you're unsure, it seems like it's not a bad idea to use one. On the left, we have the sensitivity of alpha when using the Schwarz mean compared when epsilon is 0.1. On the right, we have the sensitivity of alpha for the trimmed mean. These graphs show that both algorithms are both to some overestimation of epsilon and can even perform better when epsilon is overestimated, but sensitive to underestimation. This makes intuitive sense from our simulations, which does not guarantee our constraint on the adversary is met, and therefore there are likely times when the proportion of contaminated rewards for an action is greater than epsilon, and using alpha greater than epsilon accounts for that. Even though there is some sensitivity, all alphas used in these graphs outperform all other algorithms except for rUCB MAB, which uses optimal parameters. Both contamination robust UCB algorithms are more sensitive to misspecification of sigma, as we see in these graphs. Similar to other UCB algorithms, slight underestimation can improve performance, but large deviations from the truth can significantly degrade performance. Still, even the worst of these is about on par with it, or better than the other algorithms used, again, except for rUCB MAB, which uses optimal parameters. Thank you for listening to my talk, and here's some quick references.